going to talk about homework number 8, which was mostly about counting the number of permutations of a given cycle type. Now, this was a little bit tricky, and the main place it was tricky was if you're trying to count the number of permutations of a cycle type that's got 2 disjoint cycles of the same length, or 3 disjoint cycles of the same length. For example, things like this, 1, 2, 3, 4. That's where it gets a bit tricky. Or 1, 2, 3, 4, 5, 6, because you've got disjoint cycles of length 3 and 3. And the reason it's tricky is because when you're counting them, you could put these the other way around, right? That's the same as 4, 5, 6. 1, 2, 3. So mostly what it means is that when you do the first count, you've overcounted by some factor, and then you have to divide out again. So let's go through this slowly, starting with the general principle, which is that if you've got a cycle, just one cycle of length 3, or one cycle of length k, then what you've got in Sn, so let's think about in Sn, if you're looking at a k cycle, then you've got a choice of n elements for the first number in the cycle. You have a choice of n minus 1 elements for the second element in the cycle, a choice of n minus 2, and so on. So you do this k times because you've got k numbers. So what you get here is n factorial divided by n minus k factorial. Because, for example, if you were doing S6 and you're doing a 3 cycle, then what you want is you've got a choice of 6 elements for the first number, you have a choice of 5 elements for the second number, and you have a choice of 4 elements for the third number. Now, the thing is that we've now overcounted, because if you're a 3 cycle, then you can write your 3 cycle down in lots of different ways. Because if you're, say, 1, 2, 3, that's the same as 2, 3, 1, which is the same as 3, 1, 2. So there are 3 different ways of writing down a 3 cycle, depending on whether you start at any one of these 3 places. But because it's a cycle, it's the same thing no matter what you do. So at this point, you have to divide out. You've overcounted. You've counted each cycle 3 times here. So you have to divide out by 3. So over here, what you've done is you've counted each cycle k times, so you have to divide out by k. So that's the general principle for just a cycle. So if we look at another one in S6, a 4 cycle in S6, how many elements of that type are there? For example, here's a 4 cycle. Well, we've got 6 possible numbers for the first number. And then once we've done that, we've got only 5 left for the second number, 4 possible choices for the third number, and 3 possible choices for the fourth number. Now we've overcounted by a factor of 4, so we have to divide out by 4. So that's the principle for cycles. Now, that deals with ones where there's only one disjoint cycle. But if you've got some other disjoint cycle after it, then there's a bit more stuff going on. So for example, if you're doing something of type 4, 2 in S6, so you've got 1, 2, 3, 4, 5, 6, then you take the number of possibilities. You've got 6 times 5 times 4 times 3 divided by 4 for the first lot. Now here, how many choices have you got for this? Well, you've got 2 numbers left, because you've used up all the other numbers. You've got 2 possible choices here, and then you've only got 1 possible choice here, but again, you've overcounted by a factor of 2. So that actually this will all cancel out. And so what we see happening here is that once you've chosen the numbers in the 4 cycle, you have no choice left about which 2 numbers are going to be the transposition, which is why this one is going to come out as the same as just a 4 cycle. Now, the thing that's really complicated is if you've got 2 things of the same length. So if you have, say, 2, 2, if you're doing cycles of length 2, 2 in S6, so this is things like 1, 2, 3, 4, then you say, okay, for the first number I have a choice of 6 things, and for the second number I have a choice of 5 things, and I've overcounted by a factor of 2 because I could have started this transposition in any of 2 places. Now, for this number I have 4 numbers left that I can choose from because I've already used 2 of them up, and for this number I have 3 numbers left I can choose from, but for this transposition I've also overcounted by a factor of 2, right? But now look, because the 2 transpositions could actually switch order, I've still overcounted by another factor of 2. So I have to take half of them again. So that's what happens if you've got 2 cycles of the same length. And what's even more complicated is if you have 3 cycles of the same length. So for example, if you did 2, 2, 2 in S6, then, for example, that's something of type 1, 2, 3, 4, 5, 6. So I've got a choice of 6 numbers and then 5 numbers for these 2, and I've overcounted by 2. Then I have a choice of 4 and 3 for these 2 numbers, and I've overcounted by 2. Now, I haven't got any choice left about which 2 are going to be the last 2 numbers, because it's only the 2 remaining numbers, right? So that gives me 3 transpositions. But the thing is, I've now overcounted by some factor, because these could go in any order. And because they could go in any order, I've now got to divide out by a factor of 3 factorial. Because there are 3 factorial different ways of ordering these 3 transpositions. So I have to divide out not by 3, but by 3 factorial. So that's the basic idea for all of those. Let's do one more of them. So if we did 3, 3, if we did 3, 3, then what we've got is we've got a choice of 6 and then a choice of 5 and then a choice of 4 for the first transposition. So this is something of the form 1, 2, 3, 4, 5, 6. But I've overcounted by a factor of 3 because it's a 3 cycle. So now, for the last 3 numbers, well, there are 2 ways you can do this now. You can say to yourself, well, I've got 3 numbers left. How many different 3 cycles can I make out of 3 numbers? Oh, well, I can only do 2. If you've got 3 numbers already, there's the sort of forward cycle and the backward cycle. So now you can just multiply this by 2. And if you work out what this gives you, this cancels down to 2, so we get 1080. But another way we could do it is we could say we've got, here's our first 3 cycle, and our second 3 cycle, we've got 3 numbers left, and we've overcounted by a factor of 3. Oh, I did this completely wrong. Because the whole point of this, was that once you've counted your 3 cycles, you said, oh, well, now I've overcounted by a factor of 2 because these 2 could go in this order or they could go in the other order. So I have to divide out by another 2. So we get 40. And you see, the reason I could tell that I had done that wrong was because I was just about to do it a different way. It's always good to do things 2 ways around to make sure that you've done it right. So this way round, I chose my first 3 cycle, and then I chose my second 3 cycle, and then I said, oh dear, I've now overcounted by a factor of 2, so I'm going to divide out by 2. And if we see what this gives us, these 3's cancel, those 2's cancel, this cancels with that, and we do indeed get 40, which is the same as what we got last time. So one of the morals of this story is to try and do things 2 ways around, and do a calculation 2 ways around to check your first answer. But the main thing to remember is when you're counting permutations of a given cycle type, if there's 2 cycles of the same length, disjoint cycles of the same length, then you have to divide out by an overcount.